LangChain Pinecone Vector Stores. Description: LangChain's Pinecone Vector Store allows you to store and retrieve embeddings numerical representations of text using Pinecone, a vector database service. This enables efficient similarity search and retrieval of relevant information based on the semantic meaning of the data. Inputs: text data. This could be a list of strings, documents, or any textual content you want to embed and store. Embedding model: a pre-trained embedding model, e.g. OpenAI's ADA002 to convert your text into numerical vectors. Pinecone index: a configured Pinecone index where you want to store the vectors. You need to set up a Pinecone account and create an index beforehand. Outputs: vector database. The Pinecone index populated with your text data transformed into vectors. Similar documents: when you query the vector store with a new text, it returns the most similar documents based on the similarity between vectors. Steps: embedding: the text data is processed by the specified embedding model to generate numerical vectors. Indexing: the generated vectors are uploaded to the Pinecone index, associating each vector with its corresponding text data. Similarity search: when you provide a query text, the embedding model creates a vector representation of the query. The vector store then performs a similarity search within the Pinecone index to retrieve the vectors most similar to the query vector. Metrics: recall the percentage of relevant documents retrieved by the similarity search. Precision: the percentage of retrieved documents that are actually relevant. Latency: the time taken to perform a similarity search. Visualization plots: vector space visualization plots illustrating the distribution of vectors in the vector space. Retrieval results charts showing the recall and precision metrics at different similarity thresholds. Fine-tune parameters: dimensionality: the number of dimensions in the vector space. Similarity metric: the metric used to calculate similarity between vectors, e.g. cosine similarity. Index configuration parameters for the Pinecone index, such as number of shards and replication factor. Uncertainty methods: probabilistic embeddings using probabilistic methods to quantify the uncertainty in the generated embeddings. Ensemble methods combining multiple embedding models to reduce uncertainty. Challenges and fixes. Challenge 1: indexing large datasets. Sample use case that resulted in Challenge 1: trying to index a dataset with millions of documents can be slow and resource intensive. Fixes to Challenge 1: batch indexing. Divide the data into smaller batches and index them incrementally. Efficient data loading. Optimize the data loading process by using efficient data structures and file formats. Pinecone subset API. Utilize Pinecone subset API for efficient batch updates. Challenge 2: maintaining contextual relevance. Sample use case that resulted in Challenge 2 when retrieving similar documents. The results may lack contextual relevance, especially when dealing with diverse document types. Fixes to Challenge 2: hybrid search. Combine vector search with keyword search to improve contextual relevance. Metadata filtering. Utilize metadata associated with documents to filter results based on specific criteria. Fine-tuning embedding models. Train the embedding model on domain-specific data to improve contextual relevance. Challenge 3: handling dynamic data. Sample use case that resulted in Challenge 3: updating the vector store with new data or deleting outdated data can be challenging. Fixes to Challenge 3: Pinecone subset and delete APIs. Utilize Pinecone's APIs to efficiently update and delete data in the index. Scheduled updates. Implement scheduled tasks to periodically refresh the index with new data. Incremental indexing index new data incrementally to minimize downtime and maintain performance. LangChain Pinecone Vector Stores Pinecone. Description: LangChain's Pinecone Vector Store enables efficient storage and retrieval of vector embeddings, crucial for tasks like semantic search and question answering. It leverages Pinecone, a cloud-based vector database, for robust storage and scalable querying of large datasets. Inputs: text data, the raw text data you want to embed and store in the vector store. This could be articles, documents, code snippets, or any form of text. Embeddings: pre-computed vector representations of your input text. These embeddings capture the semantic meaning of the text, enabling similarity-based retrieval. You can use pre-trained embedding models like sentence transformers or OpenAI's embedding API to generate these embeddings. Outputs: vector database. Pinecone efficiently stores the generated vector embeddings, allowing for fast similarity searches based on query vectors. Retrieved documents. Given a query, the vector store retrieves the most similar documents or text snippets from the database, enabling information retrieval and semantic search. Steps: embedding generation. The input text data is transformed into numerical vector representations using chosen embedding models. Vector database storage. The generated embeddings are stored in the Pinecone vector database, indexed for efficient retrieval based on similarity. Query embedding. When a user submits a query, it is embedded into a vector representation using the same embedding model. Similarity search. The query vector is compared to the stored embeddings in the vector database to find the most similar documents. Metrics: retrieval accuracy evaluates how accurately the vector store retrieves relevant documents for a given query. Retrieval speed measures the time taken to perform a similarity search in the vector database. Storage efficiency assesses the storage footprint of the vector database and its ability to handle large datasets efficiently. Visualization plots. Similarity heatmap visualizes the similarity scores between query vectors and stored embeddings, highlighting the retrieved documents. Dimensionality reduction plots using techniques like tsna or PCA visualize the distribution of embeddings in a lower dimensional space, revealing potential clusters or relationships within the data. Fine-tune parameters. Embedding model. Choose an embedding model that best suits your data and task. Dimensionality. Adjust the dimensionality of the generated embeddings to optimize retrieval, performance and resource usage. Index parameters. Configure Pinecone index parameters like metric, cosine, similarity, Euclidean distance, and dimension to fine-tune search behavior. Uncertainty methods. Confidence scores. Assign confidence scores to retrieved documents based on their similarity scores, indicating the certainty of the retrieval. Diversity sampling. Retrieve a diverse set of documents that represent different perspectives or aspects of the query. Mitigating bias. Challenges and fixes. Challenge 1. Cold start problem. When the vector store is initially empty, there are no documents to retrieve. Sample use case. Building a knowledge base from scratch with no initial data. Fixes to challenge 1. Use a pre-populated dataset for initial training or manually add seed documents to the vector store. Challenge 2. Semantic drift. Over time, the distribution of embeddings in the vector store may shift, affecting the retrieval accuracy of queries. Sample use case. Adding new documents to an existing vector store that have different semantic characteristics. Fixes to challenge 2. Regularly retrain the embedding model on updated data or implement strategies for incremental learning. Challenge 3. Data scaling. Handling large datasets with millions of documents can be computationally challenging. Sample use case building a knowledge base from a massive corpus of text data. Fixes to challenge 3. Use optimized embedding models designed for large datasets. Leverage Pinecone's scalability, or implement sharding techniques. Challenge 4. Index management, managing multiple indexes with different configurations or data sources can be complex. Sample use case building a multimodal vector store that combines text and image data. Fixes to challenge 4. Use Pinecone's indexing capabilities to create dedicated indexes for different data types or use abstractions like LangChain's Vector Store Manager to simplify index management. LangChain Pinecone Vector Stores. Pinecone Vector Store. Description: the Pinecone Vector Store class in LangChain is a vector store implementation that utilizes Pinecone, a managed vector database service, to store and retrieve embeddings for efficient semantic search and retrieval tasks. Inputs: Pinecone index name, the name of the Pinecone index to be used for storing and retrieving embeddings. This index should be pre-created on the Pinecone platform. Embedding function, a function that takes text as input and returns a numerical vector representation of that text. This function is responsible for generating the embeddings that will be stored in the vector database. Text key, the key used to identify the text associated with each embedding within the Pinecone index. This key will be used to retrieve the original text when performing semantic search. ID key, the key used to uniquely identify each embedding within the Pinecone index. If not specified, a default ID is generated. Outputs: embeddings, a dictionary of embeddings stored in the Pinecone index, where each embedding is associated with a unique identifier and the corresponding text. Search results: a list of documents retrieved from the Pinecone index based on a query embedding. Each document contains the original text, the associated vector embedding, and the similarity score with the query embedding. Steps: initialize a Pinecone vector store object is instantiated with the required parameters, such as the Pinecone index name, embedding function, and text key. Add new embeddings are added to the Pinecone index by providing the text and optional metadata associated with each embedding. Similarity search: the similarity search is performed by providing a query embedding to the Pinecone index. The index returns the most similar embeddings based on the cosine similarity metric. Metrics: retrieval accuracy measures the percentage of relevant documents retrieved by the vector store for a given query. Precision measures the proportion of retrieved documents that are actually relevant to the query. Recall measures the proportion of relevant documents that are retrieved by the vector store. Latency measures the time taken to perform a similarity search operation, including embedding generation and index retrieval. Visualization plots: embeddings visualization, a visual representation of the embeddings stored in the Pinecone index, allowing for analysis of the embedding space and identification of clusters or outliers. Search results visualization, a visualization of the retrieved documents based on a given query, highlighting the relevance of each document and the similarity scores. Fine-tune parameters: dimensionality reduction, applying dimensionality reduction techniques to the embeddings before storing them in the Pinecone index, potentially reducing storage costs and improving search efficiency. Indexing parameters: fine-tuning the indexing parameters in Pinecone, such as the number of shards and replicas, to optimize for specific workload requirements. Uncertainty methods: confidence scores, providing confidence scores for each retrieved document based on the similarity score and the distribution of other embeddings in the index. Ensemble methods combining multiple search results from different embedding models or different search strategies to enhance retrieval accuracy and identify potential biases. Challenges and fixes. Challenge 1: limited storage capacity when dealing with large datasets. The Pinecone index may reach its storage limit. Sample use case that resulted in Challenge 1: attempting to store a large number of embeddings, e.g., millions in a single Pinecone index with limited storage capacity. Fixes to Challenge 1: upgrade the Pinecone index to a larger storage plan. Use multiple Pinecone indexes to partition the data and distribute the storage load. Challenge 2: high latency during search. The search performance can be affected by network latency or the complexity of the query embedding. Sample use case that resulted in Challenge 2: executing a complex query embedding that requires extensive calculations or retrieving embeddings from a remote Pinecone index with high network latency. Fixes to Challenge 2: optimize the query embedding by simplifying the model or using dimensionality reduction. Use a caching mechanism to store frequently accessed embeddings locally, reducing the need for constant retrieval from the Pinecone index. Challenge 3: data drift over time. The distribution of embeddings in the index may change, potentially affecting search accuracy. Sample use case that resulted in Challenge 3: adding new embeddings to the index that differ significantly from existing embeddings, leading to a mismatch in the embedding space and decreased search relevance. Fixes to Challenge 3: regularly update the Pinecone index with new embeddings to reflect changes in the data distribution. Utilize techniques like retraining the embedding model or performing index re-ranking to adapt to data drift.